Welcome to the WUSAT 3 platform presentation, where the team will describe and explain the work carried out this year, as well as any conclusions made and the opportunities in which to progress the project. My name is Srinivas Kalindi and I am one of the mechanical engineers on the project this year. The platform team consists of 2 more mechanical engineers, 2 electronic engineers and a computer systems engineer. The interdisciplinary team used a concurrent engineering approach to ensure that the design trade-offs and justifications were coordinated between subsystems during fortnightly problem-solving sessions. WUSAT 3 is a student project to develop a 3-unit CubeSat to be launched into low Earth orbit from the International Space Station, 400 kilometers above the surface of the Earth. A CubeSat is a miniaturized satellite used for space research to save costs, with the WUSAT model measuring 10 by 10 by 30 centimeters. The project aims to develop the RF direction-finding payload and its support subsystems on the WUSAT 3 satellite. The novel direction-finding technology is a concept offered by Rogue Manor Research for further development. The satellite will be used to demonstrate that wildlife can be observed using small RFID tags. This is particularly useful for tracking small birds for which the current trackers are too heavy. Last year's team produced a basic configuration model. This year's aim was to further the development of the satellite towards an engineering model to be used in systems testing. This is the 6th year for which the WUSAT 3 project has run and is the first year for which 2 separate teams have been assigned to the project. The objectives for each of the platform subsystems are shown. The presentation of each subsystem will provide key details about how the objectives were achieved and the results, analysis and conclusions generated. This year, the WUSAT 3 project was split into 2 teams, the payload and the platform. The payload represents the parts of the satellite that execute the mission, including the camera and RFID antennas, as well as the mechanisms built around this. The platform supports the payload by providing structure, power, telemetry, and keeps the whole satellite within operating conditions. Although we were 2 teams, there was a lot of integration between the teams, which included bi-weekly meetings to discuss our progression and solve problems together. Both teams also had systems engineering roles used to integrate all the systems between both teams and within the various disciplines.
Hi, I'm David and I'm the systems engineer with the help of Srinivas. The role of the systems engineer is to manage the various disciplines within the team, where firstly this year we maintained the requirements for each of the subsystems, updating them to be as in-depth as possible, as these are the guidelines for what each subsystem needs to achieve and where the responsibilities lie. For the first time this year, a comprehensive failure mode effects and criticality analysis, or FMECA, was also created to show where technical failure points could possibly occur based on quantitative severity, occurrence, and detectability ratings. Provisions to compensate for these failure points, as well as any additional detections provisions for these points, were then created, where a total of 41 failure points were highlighted. A critical analysis of each failure was then completed to evaluate how it may affect things outside of the satellite. For example, a critical failure while stowed on the International Space Station, potentially damaging the space station or endangering the astronauts. Another important thing to consider is the configuration of the satellite. As a team, we further developed the configuration model to ensure each subsystem physically fit within the frame without hindering the function of any of the components. From these discussions, we found that previous year's magnetometer placements, solar panel placements, and fittings would not be possible without hindering the antennas. A thorough study of different component placements was then completed for next year's team. Finally, the power, mass, data, and link budgets were maintained with this year's work to allow design decisions to be based off of. I'm also the power electronics engineer for WUSAT 3. The electrical power system, or EPS, is responsible for generating, managing, and distributing the power of the satellite. Each subsystem has power requirements for varying scenarios and is delivered power with the power distribution circuitry. When the solar panels aren't illuminated or generating enough power relative to the load, the battery will power the satellite. The EPS also needs to be controlled based on different operating conditions. An important part in justifying the EPS design decisions was to create an accurate power budget. This year, the power budget was completely reworked, evaluating the total power that each subsystem may use in the different operating modes. This was then used further to create a MATLAB script which will show predictions of the power usage over time based on different load conditions. This was used to demonstrate how the EPS control circuitry needed to manage the available power without draining the batteries below a maximum depth of discharge per orbit, highlighting a problem with the current camera system, which was draining too much power when idle. Furthermore, the model was used to justify why we need 9 solar panels as well as a 40 watt-hour battery. The EPS control circuitry is there to protect and manage the power distribution and charging. For example, this year we have implemented a circuitry that will allow the satellite to enter survival mode, where if the battery is almost fully discharged, the EPS will turn all the subsystems off using switches with redundant backups, and the whole system will just draw 0.5 milliamps to monitor whether the power is being generated again, so the power can be turned back on. Finally, the power distribution circuitry and the configuration of the EPS was designed to be as efficient as possible. For this, 3.3 volt and 5 volt regulated lines are needed where buck converters were selected for the high efficiency when compared to other types of regulators, with around 85%. Furthermore, a new low power voltage regulator was specifically designed for when the satellite enters survival mode. In conclusion, previously little consideration of the EPS and power distribution was completed. This year, we have used the enhanced power budget to fully justify new design decisions around these sections of the EPS with new capabilities and more efficient configurations. Further work is still needed to test and implement the work that's been done this year, which couldn't be done due to the ongoing pandemic. And the power budget must be continued to be maintained and ensure the power generation and usage is within spec.
Hi, my name is William Pike and I'm also one of the electronic engineers of the team, and I am responsible for the communications on the platform side of the satellite, which focuses on the telemetry and telecommand of the satellite, which is also known as TMTC for short. The purpose of the TMTC system is to be able to send commands to the satellite and to receive responses such as telemetry and status information from the satellite. We will operate in the amateur satellite frequency bands, and therefore we are subject to strict licensing requirements. This subsystem is critical for the functionality of the satellite, as it is the system which will tell us if the satellite is alive, therefore reliability is key. This year's work was focused on continuing the component choice effort from last year's team. Therefore, to ensure reliability, we ensured that each component of the TMTC system is compatible with each other and that they function for our requirements. This figure shows the flow diagram of each component chosen from top to bottom. Most of the system is made by GomSpace, a Danish satellite equipment manufacturer, more precisely both the satellite side and ground station transceivers, to ensure compatibility of modulation and packet formats, as well as reliability with good data rates. The link budget was also updated using these new component choices, whilst continuing to use the orbital analysis parameters as recommended by last year's team, which follows the European Space Agency's recommendation of 3 cases as shown here: favourable, nominal and adverse. The link budget summary table shows that we have a 21 dB minimum margin currently compared to the noise floor in adverse conditions. The datasheet for the transceivers used states that this margin means that we can expect a data rate of around 38.4 kilobits per second. This, however, depends on our bandwidth allocation from AMSAT UK, which is UK's Amateur Satellite Society. Our main transmission channel parameters are shown here in this table, specifically which frequencies we plan on using. There are still some details which are not final, mainly the modulation scheme, which needs more research to find which one best suits our requirements, and the bandwidth, which depends on how much we get allocated through licensing. An amateur satellite license allows us to have a private connection to the satellite for the uplink, such that only we can control it. However, the telemetry must be public, such that anyone can listen to the data we request from the satellite. Looking back on the work achieved this year, we can recommend directions in which more work needs to be completed for this subsystem. Due to COVID, the antennas were not able to be built and tested this year. This needs to be done to also be able to design the matching network for the antennas. Research needs to go into the modulation schemes and the effect of Doppler shift to improve our reliability. To note, the MATLAB Satellite Communications Toolbox was released only a couple of weeks ago. This also could help future teams with orbital analysis and testing the reliability of our transmission. Finally, licensing efforts and contact with GomSpace needs to be continued. In the project, I am also responsible for the Attitude Determination and Control System, or ADCS. The main purpose of the ADCS system is to detumble and point the satellite after the deployment from the ISS. This is required as after being deployed from the ISS, the satellite has a random angular velocity in all 3 rotational axes. These need to be reduced to 0. The pointing functionality is needed as the payload requires the main satellite face, as shown here on the right, to be pointing directly towards Earth, otherwise known as nadir pointing. The mission required that the ADCS also provides stable pointing for the payload camera to capture clear images, reliability with redundancy, autonomous operation, as we will not have constant contact with the ground station, and finally it needs to function without any form of propulsion system, as we are not allowed fuel. Previous year's teams have attempted to design and manufacture ADCS systems themselves. However, the nature of the problem is too complex for the scope of this project. Therefore, last year's team decided on a commercial off-the-shelf, COTS for short, system by CubeSpace Limited. This year's work was therefore focused on deciding which configuration of the Cube ADCS system from CubeSpace is optimal for our mission requirements. The final configuration of the ADCS system component choices was helped thanks to CubeSpace, which graciously ran simulations using our mission requirements, which included the moments of inertia as well as the solar panel and antenna placements of our satellite. Therefore, we will be using the Cube ADCS Y Momentum ADCS system from CubeSpace Limited. Looking back on the work achieved this year, there are a couple elements of work that still need completing. This includes the physical placement of the ADCS system components in and on the satellite. Also, work needs to go into the control and interfacing of the ADCS system, such as understanding the I2C commands between it and the OBDH. And speaking of OBDH...
Hi, I'm Michael, responsible for the Onboard Data Handling System, OBDH. The OBDH is responsible for coordinating operations and handling data for other subsystems. It is a key element for controlling and maintaining the safety of the spacecraft. Historically, the OBDH was considered part of the TT&C, but with the increased responsibility it plays in modern satellites, it is now treated as a separate subsystem. In WUSAT 3, the OBDH is responsible for storing platform and payload data, receiving, decoding and executing telecommands, coordinating the downlink of telemetry data via the TMTC, managing and distributing a local time signal, and maintaining the health of the satellite by monitoring sensors. In terms of practical development this year, the aim was to start migrating the functionalities of the demonstration model to more appropriate hardware as the Raspberry Pi was previously used. Furthermore, the objectives were to create a data budget, define interface requirements, solve the timekeeping problem, and define a method to store platform data. A data budget was started to keep track of the amount of data stored on board the satellite, shown in the bottom table. This should be updated as subsystems update their data needs and polling rates. The diagram above summarizes some of the protocol, control, and monitoring requirements, along with the hardware interfaces needed to integrate the OBDH within each subsystem. These were key metrics when making hardware choices for the OBDH. Different hardware options for timekeeping were analyzed considering cost and the required accuracy. Using a dedicated real-time clocking calendar module such as the MCP7940 came out on top as it frees the main CPU for time-critical tasks and achieves a low error of around 60 seconds per year. The module can also be provided with an alternate power source such as a small lithium battery for situations when the EPS is down. A circuit schematic was created connecting the module, a crystal oscillator and a microcontroller over an I2C connection. A number of data storage devices were considered, such as SD cards and memory on board the microcontroller. Using the data budget to estimate the required storage and considering the low power of the microcontroller, EEPROM chips were chosen for non-volatile storage. Based on previous year's research, a PIC16 microcontroller was used as it is low power, budget friendly and has a heritage in CubeSat OBDHs. To bring together and conclude the hardware choices, the demonstration module was updated using the PIC16, the EEPROM memory chip, the RTC, and an LM35 temperature sensor used to create part of the active thermal monitoring system. The model was able to take a measurement from the sensor using an analog to digital converter, calculate the corresponding temperature value, and then store this in memory. It could then retrieve the value and output to a terminal over a UART connection. Some practical testing could take place using the hardware components. However, due to COVID lab limitations, it was easier to develop and test code using a circuit simulator. For future work, next year should attempt to verify the results found this year. They should add new hardware components, such as the EEPROM, to the PCB schematic, work with mechanical engineers to integrate an antenna deployment mechanism, and consider whether implementing the CubeSat space protocol for telecommands is within the scope of this project.
Thank you, Michael. My name is Pierre, and I'm in charge of the structure subsystem. The structure subsystem is responsible for the design of the chassis and the external panels, as well as the physical integration of all components together with the chassis. The 3-unit CubeSat will be placed with another similar CubeSat in a larger housing during the launch and until deployment. This housing is called nanoracks, and it gives some of the main driving design factors for the CubeSat structure. The nanoracks also include some deployment features that had to be designed to respect the deployment process. This includes the remove before flight pins, the separation springs, and the deployment switches. The aim for the structure subsystem this year was to improve on last year's chassis design while managing any configuration changes. Because the product is in transition from configuration model to engineering model, it was crucial to include in the design process the manufacturability of each component and fittings. The aim was also to investigate the nanorack's requirements and operation, and to start designing and integrating components to the rest of the structure. The outcome of this year's work were that the material used for the chassis have been chosen after a mechanical and thermal analysis done with Srinivas, and the material used will be aluminium 6061. Stress, displacement, and dynamic analysis have been undertaken at each stage of the design to ensure that the structure respected the load and vibration requirements. The structure design has been chosen from several design options and further refined to be realistically manufactured. Manufacturing of the main structure has begun and will be completely done by the end of Term 3. And finally, nanoracks requirements have been reviewed and updated, and design have been created on CAD for every component. An iterative design process have been undertaken for the rails design. The process included 3 new designs, each aiming at improving on the last version and complying both to manufacturability and structural requirement. The final design, Design 3, respects all requirements, in that one rail can be manufactured in one piece. Also, it is the easiest to manufacture because it uses cutting over machining. This allows more precision and less residual stresses. In terms of configuration, the third design enables easy implementation of the shelf rod fittings and the TMTC envelope on the lower end of the satellite. The nanoracks deployer is what allows the CubeSat to be deployed in low Earth orbit. This year, nanoracks development has focused on understanding the deployment process and designing its physical components, so the RBF pins, the deployment switches, and the separation springs. The driving factors for designing the RBF pins was that it must remain in during the launch and should only be pulled out manually by the ISS crew just before the nanoracks deployment. The deployment switches are the actuators that close the power circuits and allow a timer to be started before the satellite enters operation mode. The deployment switches are located on 2 opposite ends of the rail's Z face. They will be actuated when the nanoracks housing deploys the satellite into space, pushing the deployment actuating rod inside. The driving factors for designing the separation spring were protecting the satellite from violent contact with other satellites and not creating space debris. The power requirement established in the power section state that WUSAT needs 3 solar panels per phase. To fit those, an option considered was to put deployable solar panels on the top and bottom, so that there could be 3 solar panels on the left and right face of the satellite. But deployment mechanisms still need to be developed. A similar type of deployment mechanism as the one used for antennas should be prioritized. This has some consequences on the magnetometer placement. The latter should be placed on the nadir face if deployable solar panels are chosen. Further work to be done includes a more advanced abacus analysis, including bolt stress. Next year, teams should perform a load and vibration test on the chassis currently being manufactured by using dummy loads for internal components. Further change to the structure shall be done if the manufactured one doesn't pass those tests. Finally, slider or roller deployment switches for the nanorack shall be more investigated. I'll now pass on to Anirudh for the TMTC deployment mechanism.
Hi, my name is Anirudh and I am responsible for designing the TMTC deployment mechanism this year. The telecommunication and telecommand deployment mechanism is used to deploy the uplink and downlink antennas. The antennas need to be deployed to allow for the best gain. A high gain would not be possible if the antennas are operating in their stowed state. This year, the team re-engineered a commercial off-the-shelf deployment mechanism, as seen on this slide, which ISI Space currently sells. The COT system currently costs in excess of £5,000 and is overly complicated as it implements thermal sensors. Instead, a simplified burn wire mechanism was CAD'd, as it was deemed that I2C command could be used to trigger the burn wires via the OBDH. Here you can see a CAD render of the TMTC mechanism in its rolled stowed state, as well as the dual redundant burn wires. Here you can see another CAD render of the TMTC antennas in their deployed state, as well as the antenna cables. To bring the deployment mechanism to fruition, the electrical circuit needs to be created in a virtual environment, and suitable components need to be selected, such as a microcontroller. The microcontroller needs to be programmed to trigger the burn resistors via an I2C input. As shown on this slide, a wiring schematic is shown for a quad antenna setup. This needs to be modified for a dual antenna setup. Also, the PCB needs to be printed, and the aluminium housing for the deployment mechanism needs to be milled. Next, the thermal subsystem will be discussed by Srinivas.
Thank you, Anirudh. My name is Srinivas Kalindi, and I will be presenting the thermal control implemented on the WUSAT 3 satellite. Thermal control of a satellite is used to ensure that the internal and external components used for the mission remain within their operating temperature ranges described by the European Cooperation for Space Standardization, ECSS, despite the harsh conditions present in low Earth orbit. These include temperatures as low as 4 Kelvin and large amounts of radiation from the Sun and Earth. The CubeSat design will be tested using simulations of simplified models. The key requirements for the thermal subsystem include that, firstly, the thermal control must be achieved by mainly passive means. Additionally, the thermal subsystem must not impose any constraints on any other satellite subsystems. The thermal subsystem is limited by the lack of mass and volume available in the CubeSat design. The previous year's thermal subsystem work focused on the temperatures experienced by the outer chassis panels and rails of the satellite during multiple orbits. The use of AZ93 white paint was modelled to generate stable temperatures throughout the orbits. The mathematical model developed over previous years and improved this year enables simple thermal analysis of the outer structure to be completed. However, due to steady-state calculations being implemented, the results generate unrealistic temperature stability for the satellite. The main thermal analysis was carried out using ESATAN, which is a specially designed thermal modelling suite used for satellites. This software allows for all material properties to be inputted manually, unlike Fusion 360 and SolidWorks, which limit the material customization possible. ESATAN also allowed for the properties of the internal components to be simulated, generating more accurate and complete results. ESATAN software allows for complete orbit analysis and is able to calculate view factors to accurately determine the heat flux on each surface of the satellite. The main aim of this year's thermal control was to ensure that the internal components of the satellite are kept within their required operating temperature ranges during all phases of the mission, including during the battery survival mode when heaters cannot be used. The results generated by the simulations show that the internal component temperatures remain within the operating temperature ranges throughout the first orbit only when thermally isolated from the outer chassis. Otherwise, the temperatures of the components drop below the minimum operating limit due to the need to wait 30 minutes after deployment before the battery and heaters can be switched on. The design of these thermal isolators must be researched and implemented into the satellite. Further work for the thermal subsystem will include modelling the temperatures of deployable solar panel mechanisms, understanding the effect of thermal bridging brought on by the wires connecting the deployable patch antennas, as well as physically testing a functioning engineering model in a thermal vacuum chamber to simulate the effects of low Earth orbit. In conclusion, the development of the configuration model towards an engineering model will be continued over the next year, with the primary focus being on designing the deployable solar panel mechanisms and accommodating the wiring between electrical components. The integration of electrical components within the satellite will be aided by the progression of a FlatSat, which is a functional representation of the electrical systems, accommodating configuration, engineering and flight model components. The development of an engineering model will allow for systems testing and drive progress to the final flight model stage of the WUSAT 3 project. The handover documentation ensures complete knowledge management to next year's team, allowing for progress and lessons learned to be clearly communicated. Thank you for listening to the WUSAT 3 Platform Team presentation.